Welcome back, everyone, and this will most likely be the last video for this lesson. So unfortunately, we're not going to be able to get through this entire section, but that's all right. I'd rather take it slow through it. So what we have here is we have another question, and this one's going to very closely resemble some of the questions that you have done before, especially with your equilibrium constants, in order to figure out the final equilibrium concentrations. This is essentially the exact same thing. We're going to be using the rule of 100 in order to solve this equation or this question. So we'll take it nice and slow through it just to make sure that everybody's on the same page. Feel free to pause the video at any time if you need to, if people are falling behind, but we should be good to go. So when we look at this question here, whenever I see Ka values that are very small, like this one, 10 to the negative 4, 10 to the negative 5, even 10 to the negative 7, you're going to immediately think that it is a weak acid. With these very small Ka values, we immediately know that HF, or hydrofluoric acid, is a weak acid. So what we're asked to do is calculate the pH of a solution that is 1 mole per liter of hydrofluoric acid. So with these ones, there's a few kind of general steps that we need to go through to make sure that we are calculating the right thing. The very first thing, we've already looked at our Kw values. All right? So with our Kw, as you may recall, it equals the concentration of our H plus ions and multiply them by the concentration of our OH minus ions. And typically this value is going to, or it always equals 1.0 times 10 to the negative 14. Right? And generally it is a 50-50 split, as I said before, so our H plus ions are going to be 1.0 times 10 to the negative 7, right? And that's moles per liter. And our OH minus ions are also going to be 1.0 times 10 to the negative 7 moles per liter as well. So for each of these, we are going to notice that just in generally water, we're going to see that there are some moles or some particles of H plus being produced even without HF being introduced. So the very first thing that we need to look at is to make sure that water is not producing a significant amount of H plus ions, because if it is, we have to consider that these ions are going to be produced, right? So what we will typically do is we just compare our Kw to our Ka, right? And as we see here, our Kw is going to be 1.0 times 10 to the negative 14. And our Ka, as we see up here in the question, is 6.6 times 10 to the negative 4. So by looking at these, 10 to the negative 14 and 10 to the negative 4, we can say with pretty good certainty that the majority of our H plus ions are going to be coming from here, because this is a much larger number by an exponent of 10. So we can say with certainty that all H plus ions, or I shouldn't say all, the majority of H plus ions are going to be coming from our H plus, HF. Right. So with this, we can look at this and go, okay. And most of the times you aren't going to get a question where you're going to get the majority coming from your water, just because this constant is so low. However, sometimes they may throw a curveball in there. I don't think I'm planning on throwing you a curveball like that, but it's always good just to check, just to make sure that you do know that the majority of the H plus ions are going to be coming from your HF. Once we know that, again, like we've always kind of done, make sure we're just quickly writing out our balanced equation, right, or our net ionic equation, I prefer to write instead of writing the H2O in. So we're having HF, which is going to be aqueous, and it is going to react in equilibrium to produce H plus ions and fluorine minus ions, okay, both of which are going to be aqueous. So looking at this, we can immediately take this reaction here and create our Ka equation. So we know that Ka is equal to, like we've seen many times before, right, H plus A minus all over the concentration of HA. And in terms of this equation, it equals the concentration of H plus times the concentration of F minus, all divided by our concentration of HF, which is all aqueous given the start of the reaction. So with any of these equations, just as we've seen before, we always throw them in a nice table just to make sure that we have everything lined up, especially when we are going to start going through and solving for X, our change in concentration. So I'm going to quickly construct a nice table here, just so we have everything in front of us, so that we can always look back and see if we need to gather any more information. A lot of the times this ICE table is going to be where we can get it. So we have our HF, which is aqueous. We're going to have our H plus, and we are going to have our F minus. Right? In each of these reactions, we know our initial concentration of our HF can be found here at the top of our page. It is going to be 1 mole per liter. Right? So we are going to look here. We're going to go 1.0 moles per liter. Right? And our H plus, we're assuming this is before we've dissolved any of this HF into water. So our H plus is going to start at 0. And our F minus is also going to start at 0. Because this is a 1 to 1 to 1 ratio, we know that HF is going to be minus X, H plus is going to be plus X, and F minus is going to be plus X as well, giving our equilibrium concentrations of HF to be 1.0 minus X. Our H plus is just going to be X, and our F minus is also going to be X. So what we can do now is we can use this Ka equation in order to solve for our X. So if I take our values from over here, our equilibrium values, and sub them into this equation, it is going to give me that my Ka, which is 6.6 times 10 to the negative 4, is going to equal the concentration of H plus, which we get from right here as being X. The concentration of our F minus, which we get right here, is going to be X as well, all divided by 1 minus X. So as soon as we get to this part here, we get a little bit nervous because we know that this X and this X are going to multiply together to give us X squared. And down here, we are not going to have a square. So as soon as we see this, we automatically start thinking quadratic equation. And at all times, we want to be lazy. We want to avoid using the quadratic equation unless it's absolutely necessary. So what we can do is we can use our rule of 100 in order to see if it's going to be applicable for us to use our simplification or our assumptions. So remember, for our assumption, it has to be greater than 100. The concentration, right, or the initial concentration of HF over our Ka, which is 6.6 times 10 to the negative 4. All right, I just got that from up here and brought it down here. And if we look at that, I take it into my, or I'll first put it in. Our concentration of our HF, our initial concentration is 1.00 moles per liter divided by 6.6 times 10 to the negative 4. And that is going to give us a value of 1.0 divided by 6.6 times 10 to the negative 4. And that's going to give us 1.515 times 10 to the 3, or 1,515, which is going to be much greater than 100. So seeing that, all of a sudden we can make an assumption. That assumption is that this change in X in comparison to this 1 mole per liter that we're starting at is going to be very, very, very small. So say it is a very, very small number. Even if we have, if I go down to the bottom here, if I have 1 mole per liter and I subtract, let's say 1 times 10 to the negative 5 from that 1 mole per liter, it's still going to equal approximately 1 mole per liter, especially if we're using our significant figures. So what we can do here is we can actually make the assumption that this x here, or 1 minus x, we can just kind of get rid of this x, right? And our assumption is that 1 minus x is approximately equal to 1, right? And we will carry that forward into our next equations. So if I move on to the next page here, once I start using that, all right, I'll put it back into our Ka equation. So 6.6 times 10 to the negative 4 is going to equal X, which is our concentration of H plus, times the concentration X as well for our concentration of F minus, all over our concentration of HF, which is going to be 1.0 times, or minus X, right? But we are eliminating this X value, so we're no longer going to use it. So instead, our new equation is going to equal 6.6 times 10 to the negative 4 equals concentration of X squared, so I just multiplied this one by this one, gathered like terms to give me X squared, over 1.0. When we see 1.0 in the denominator, that makes us very happy, because in order to get rid of that, I just have to multiply both sides by 1. Obviously, if I multiply 6.6 times 10 to the negative 4 by 1, it is still going to equal 6.6 times 10 to the negative 4. So essentially, we can really just get rid of this 1.0 altogether. So we'll actually have 6.6 times 10 to the negative 4 equals the concentration of X squared, right? And that makes it quite easy from here out. All we really have to do, we're going to square root both sides. When I square root this, it's going to get rid of the squared, get rid of the square root. So, in other terms, our square root of 6.6 times 10 to the negative 4 is going to be equal to X. So, if I take my calculator, I'm going to put 6.6 times 10 to the negative 4, and I'm just going to square root it. If you can see here on my calculator, I'm just going to square root that value, answer, and that is going to give me 2.57 times 10 to the negative 2. So that is telling me that the change in concentration of both our F minus and our H plus ions is going to be 2.57 times 10 to the negative 2 moles per liter equals X. And if we go back to our ICE table, we see that X here is the change in concentration. So we know that both H plus and F minus are going to have final equilibrium concentrations of X, which is equal to 2.57 times 10 to the negative 2 moles per liter. So using that value there, what we can do is we can actually now input that, right, in order to find, actually what we should do first here is actually do our 5% rule to make sure that we have made a correct assumption. So what we can do, just to make the 5% rule a little bit easier, if we just take our x value that we find and we divide it by the initial concentration of HF, as long as this value is less than 5%, we can make our assumption correct, right? So if our x value is 2.57 times 10 to the negative 2, and we divide that by our initial concentration of 1 moles per liter, that is going to give us 2.57 times 10 to the negative 2 times 100% is going to equal 2.57%. So that is less than this 5%. So we can say that yes, our assumption is good. So finally, once we have made that correct assumption, now we can actually solve for our pH, which was what it asked for in the very start of the equation. So as we know, again, pH is equal to the negative log of the concentration of H plus ions. Now, looking back at our ice table, right, our equilibrium concentration is just going to be equal to X. So I can just input this X value here into this equation in order to solve for pH. So pH is going to equal the negative log of the concentration of H plus, which is equal to 2.57 times 10 to the negative 2 moles per liter. So our pH, if I put it into my calculator, we're going to see that our pH is the negative log of 2.57 times 10 to the negative 2 moles per liter. If I press equals, all right, that is going to give me a pH of 1.59. So I can put that in as my final value. All right, and that is the final answer. So what we're going to do now is there's one more sample problem in the textbook, and I'd like you to try and work through it on your own or in partners. It's not going to be marked or anything, but if you do have a bit of time at the end of this class, it is sample problem 2. Right, and it is on page 518. With this sample problem, it gives you every step along the way. I'd prefer if you would try it first, and if you get stuck, then go through the steps in order to determine where you might have made a mistake. Just be careful, that rule of 100, if it doesn't equal more than 100, you cannot make the assumption and you may have to use the quadratic equation. All right. Once you're finished that, you can also try practice problems numbers 1 and 2 on page 520 of your textbook, and try those for homework and make sure that those are completed. Tomorrow what we will do is we will continue on in section 8.4 in these same video sets. If you would like to, or you're not planning on being here tomorrow, make sure that you watch the videos ahead of time. They'll all be posted as of today for you guys, so you'll be able to watch all of the videos ahead of time. I really do hope these videos helped, and stay tuned for part 4 tomorrow.